Welcome to another edition of Math for No Reason. In this edition, we are looking at this problem which asks us to show that if f is a continuous function on the closed interval 0, 1 such that the integral from 0 to 1 of x power n fx dx is equal to 0 for n equal to 0, 1, 2, etc., then the function f is equal to 0 for all values of x in the closed interval 0, 1. Now, to prove this result, we will invoke the very well-known Weierstrass approximation theorem. What does this result say? This result tells us that given any continuous function on a closed interval ab, in this case a equal to 0 and b equal to 1, then there exists a sequence of polynomials Pnx such that Pnx converge to f uniformly on the closed interval ab. That means if n is large, Pnx minus fx is less than any arbitrary quantity epsilon for all n larger than some value capital N and for all x belonging to the closed interval a to b. So, this result, which is a very important result, is known as the Weierstrass approximation theorem. It tells us that every continuous function can be approximated by using polynomials for all values of x within the closed interval ab. So, we will use this result in this case. Now, also observe that if you have Pn converging to f uniformly on the closed interval ab, then Pnf converges to f square uniformly on this same closed interval ab. So, whenever Pn converges to f uniformly on the closed interval ab, then Pnf would converge to f square uniformly from the closed interval ab. Now, we keep these results in mind and approach this problem. Suppose Pn converges to f uniformly on closed 0, 1. Now, since Pn is a polynomial, so we can write Pn as some a0 plus a1x plus a2x square, etc., plus ak power. So, this Pnx we are assuming is a kth degree polynomial. Now, what is the integral from 0 to 1 of Pn into f? So, we see that this is equal to a0 plus a1x plus a2x square plus akx power k fx. By using the usual rules for integration, this becomes a0 into fx dx plus a1 into integral 0 to 1 x fx dx, etc., plus ak into integral 0 to 1 to the power k fx. And by the given hypothesis, integral 0 to 1 fx dx is 0. So, this is a0 into 0. Integral 0 to 1 x fx dx is also equal to 0. So, a1 into 0, etc. Integral x to the power k fx is equal to 0, again by the given hypothesis. So, this is ak into 0. So, this is equal. So, this is a very important result to note, that integral 0 to 1 Pnf is actually equal to 0, and this is true for all n. Now, we will use this result. So, let us remember this result, that if Pn converges to f uniformly on an interval, on a closed interval, then Pnf converges to f square uniformly on the closed interval 0, 1. So, since Pnf converges to f square uniformly on closed interval 0, 1, the integral must also converge. That is a very well known result. So, we have integral of 0 to 1 Pnx fx dx must converge to integral 0 to 1 f square x. However, we have just now seen that the left hand side here is 0. So, 0 converges to integral 0 to 1 f square x dx. Now, this can only happen if integral 0 to 1 f square x dx is equal to. So we have shown that integral 0 to 1 f square x dx is equal to 0. Now, since f is continuous, f square is continuous and it is non-negative. So f square is continuous and non-negative. Integral of a continuous non-negative function being 0 means that the function itself must be 0 for all x. This is what we are required to prove. Thank you.